So thank you, Pierluigi. Thank you for the other organizers. I'm very pleased to be back in Paris and IHP. I haven't been in either place for a few years. So one reason I prefer that it be called Riemann hypothesis rather than number theory is I don't really know hardly anything about number theory. I know a little bit about the Riemann hypothesis. So, especially this first talk are, I think, designed so that you don't need to know hardly anything about any of the topics in advance. So obviously one topic is the Riemann hypothesis. The connection that I'm interested in, a possible connection with statistical mechanics, has to do with a theorem of Li and Yang, which I'll tell you about. Which has to do about zeros of partition functions of certain kinds of statistical mechanics models. And the possible connection between the two has to do with distributions of block magnetization variables. So that's today's discussion is about these three topics and the beginning of discussing possible relationships. Then so this is the outline of the series. The second talk will focus on this Li and Yang theorem, and in its original, more or less original version, which are theorems for statistical mechanics spin systems where the spin variables are one component, that is one-dimensional variables. In particular, Ising type spins. And during the various lectures, some things will actually be stated as theorems, some things will be stated as kind of quasi-theorems, and some of the things are stated as theorems. I actually will spend the time to give proofs, and that will be the case over here. Most of what I talk about is fairly old. Some things less old. And of course, the interesting questions have to do with things that haven't yet been done. Here are a few references for this lecture. So there's an old paper of mine, Communications, Pure and Applied Mathematics, Volume 27, 1974. There's a paper of Lieb and Sokol, Communications and Mathematical Physics, Volume 80, 1981. There's a recent survey article about Li-Yang type theorems of Froelich, relatively recent, of Froelich and Rodriguez. That's Journal of Mathematical Physics, 53, 2012. The third talk will be about block magnetization of variables in Ising models, and in rather simple cases, simple scaling limits of Ising block magnetization. And the simple models are not interesting from a statistical mechanics or physics point of view, but they're cases where you can carry through things easily and exactly, and they begin to give you a flavor of what might be true in other cases. And the two cases here are the Curie-Weiss model and the one-dimensional Ising ferromagnet, which is boring physically, doesn't have a phase transition, but still you can study its block magnetization. Something which is much less trivial, and this is the one thing which is much more recent result. That's discussion of scaling limits of block magnetization for the 2D Ising model, two-dimensional Ising model, and some information about what they look like. Then the last talk has to do with extensions of some of these ideas, theorems like Liang type, and some ideas for the case of two-component spin systems. Sometimes called XY models, or XY spins, sometimes called classical rotor or rotator models. These are where the spin variable, instead of taking values in +1 or -1 or on the real line, take values, say, on the unit circle. So the spin dimension, which is 1 or 2, is different than the spatial dimension, which can be 1, 2, 3, 4, etc., although we'll mostly talk about 1 or 2 in that case as well. So this has 3 parts. There's just probably a statement, probably without proofs, of the Liang theorems, or Liang type theorems. These weren't actually done by Li and Yang, who only studied the Ising models. And some references to Liang theorems for two-component spins. There's, I think it was originally done in a paper of myself and Francois and Lap. Is that the right way to pronounce it in French? The names are hard to say. I should say Dunlop, but it's probably Dunlap. Anyway, I should know that since he was a co-author, although we actually weren't in the same continent at the time we did this. That's communications, mathematical physics, before 1975. And then these things are also discussed in the second two of these references, plus Lieb, Sokol, and the Frola Rodriguez papers. Like in the case of one component, Ising spins, it's convenient, it's useful to think about a very simple case first. which is the, here is the one-dimensional. You can also do the Curie-Weiss, but that's really no different than the one-component case. The one-dimensional XY model, you can express things more or less explicitly, and that's worth looking at. One spatial dimension. Scaling limit in this case, in the Ising case, is expressed in terms of a one time dimension, which is used to be the one spatial dimension, Markov jump process that jumps between +1 and -1. In this case, the corresponding thing is a one time dimension process taking values on the unit circle, which is basically a Brownian motion wrapped around the circle. And then hopefully there'll be a little bit of time to talk about speculations about what might happen for the two-dimensional XY model, which should be related to the two-dimensional Gaussian free field and other things that are very popular, and maybe has something to actually do with the Riemann hypothesis, maybe. Okay. So, so as I said, I'm going to try not to assume that, or try to assume that at least some people in the audience who don't know hardly anything about any one of the particular topics that I'm talking about. And so I'll tell you more or less what you need to know. The Riemann hypothesis concerns zeros in the complex plane of Riemann's zeta function, which initially can be defined just as the infinite series n to the minus s. So you originally defined this for s real and bigger than 1, where this is convergent. Easily seen that it's still convergent for s complex if the real part is bigger than 1. And then it's a classic fact that that function of complex s for real s bigger than 1 can be analytically continued to the rest of the complex plane. And is analytic there except for a pole it's also known to have equals 0 at certain negative integers. Those are called the trivial zeros. And the Riemann hypothesis is a conjecture about where all the other zeros are. So all the other zeros lie on a vertical line that passes through s equals 1/2. That's the so-called critical line. So this originates, it comes from number theory because properties of the zeros are closely related to the distribution of prime numbers. And I'm not going to say anything about that because there are surely many people in this room who know about that stuff much more than I do. So I just take it as a given that this is considered to be an important open problem. Okay, so now I'm going to define a function of a real variable that the first time you see it looks just strange, but it's also kind of well known, not always written, sometimes written exactly the way I'm going to write it, sometimes written somewhat differently. It's a kind of change of variables of a theta function with a few other things, and I'll explain how it's related to the Riemann hypothesis. Yes.
So if you say from trivial zeros and -2, -4, -6, so if I plug in minus s equals -2, I get some n squared.
Well, you can't. No, you can't plug it in. This formula only works when real part of s is bigger than 1, but one can prove that that function, even though it has a pole at s equals 1, it blows up as you approach that, obviously, it somehow has an analytic continuation to the complex plane, and that analytic continuation at s equals -2, -4. But this formula doesn't work anymore once you get to other than real s bigger than 1. Okay, so here's this function. So it's a function of a real variable x. As you'll see in a moment, it's defined for all real x as a specific complicated-looking infinite series. Let me leave. There's a prefactor that's a little complicated. I never leave enough room for it, but we'll see. E to the minus n squared pi e to the 2x. Okay, so for any real x, e to the 2x is positive, and so these coefficients go to 0 very rapidly with n. So you can put in here coefficients that grow with n as long as they don't grow too fast. And what you put in is the following strange thing. 4n to the 4th pi squared e to the 9x over 2 minus 6n squared pi e to the 5x over 2. So for a particular value of x, these are some positive numbers. So this is growing like n to the 4th, and so this goes to 0 so fast that that's certainly summable. And so you get a number for each x that defines this function. Okay, so obviously, I wrote this because it has something to do with the Riemann hypothesis, so let me tell you what it has to do with it. In particular, how is this function psi related to the zeta function? It's related by its two-sided Laplace transform. So this function, at the moment, you can see from this formula that as x gets large, because of this factor, this gets very small quite rapidly in x. It's not quite so clear what it does for large negative x, but I'll explain in a moment why we know that it also gets small for large negative x. That's hard to see from the formula. But because it does, then you can do this two-sided Laplace transform for any, not just real z, but actually complex z, because this will be rapidly decreasing both at plus infinity and minus infinity in x, with psi. And that defines a function called Riemann's C function. I always have trouble distinguishing between the chi and the xi. And Riemann's C function is related to the zeta function by the following formula. So that gives the relation of this function to the zeta function. It's s minus 1 pi to the minus s over 2, the gamma function of s over 2, zeta function of s divided by 2. And the only thing that's missing is what's the relation of z with s. And that's the following. Let me put that in here. With z, or with s, equals z plus 1/2. Okay, so you take the zeta function, you multiply it by a gamma function. The gamma function has some poles at negative integers, which correspond to negative even integers of s. Those poles sort of cancel the zeros of the trivial zeros of the zeta function. And I guess, yeah. And the zeta function has a pole at 0, which I guess is canceled by a 0 of the gamma function. So the one thing this does is gets rid of the trivial zeros in the pole. And then this stuff, oh, sorry, no, the 0, 1, sorry, that was this one. Sorry, excuse me, that was this one got rid of the pole. Anyway, somehow or other, this thing gets rid of all those trivial zeros in the pole. And then this extra factor somehow manages to make, as I'll mention in a second, something called Riemann's functional equation for the zeta function, which for the C function is simply the statement that C is an even, sorry, this should be a, yeah, no, I guess that's right. That C is an even function of Z with this change of variables. Oh, yes. And this change of variables takes the critical line, which was real S equals 1/2. That makes it real Z equals 0. So the critical line in the Z variable is the pure imaginary axis. So critical line. Real Z equals 0, the pure imaginary axis for Z. Okay, so anyway, you can kind of forget this intermediate thing. This is the relation between this weird function of x through a two-sided Laplace transform and the zeta function. So here's what you actually need to know. And they're all well-known and quite old. I don't know exactly how old. Early part of the 20th century, maybe, or so, maybe even earlier. So these are facts about this function psi and its Laplace transform. So one is that this function psi, even though it does not look like it at all from the formula, is an even function of x. We'll use that all the time. That's the same as, if all my notation is right, that's the same as a slightly different looking property in this variable, which is that this C function is related to, it has this symmetry, and that is that's written in terms of the zeta function. That's called the Riemann's functional equation for the zeta function. So this, as I said, this formula, this is completely unobvious from the formula. Okay, but let's already start using it. I was actually using it already before without saying even less. And now I'll use it to justify the thing I said before, that it's easy to see from the formula that this function of x decreases very rapidly for large positive x. It's not clear what it does for large negative x, but you don't have to think about that once you accept this. So hence, this function psi of x is rapidly decreasing as x goes to infinity. Basically like, well, this one, it's dominated by this factor, and that one is the least decreasing one of those is n equals 1. So it's basically like e to the minus some constant e to the 2x. So originally for a large positive x, but it's even, so it's the same for large negative x. And the c, I guess, is pi. Okay, this will keep on coming back in our discussions. And then finally, because one has gotten rid of the trivial zeros and one has moved the critical line to the imaginary axis in the z variable, then the Riemann hypothesis is now simply the statement that the two-sided Laplace transform of this very specific function, all of its zeros. So this is, because this decreases so rapidly, this is defined for all complex z and is an analytic function of z. So it has zeros somewhere, or if can't have zeros somewhere, and we'll have to have zeros. And the Riemann hypothesis is simply the statement that all the zeros are purely imaginary, because that's now the critical line in this variable. So I'm going to use this phrase so often that I will abbreviate it to PIZ for pure imaginary zeros, or the pure imaginary zeros property. Okay, so that's sort of the background, and that's pretty much what you need, or what we need to kind of keep going. And now we're going to observe something where we'll again use this property, and I don't know. I'm not sure. This is a less well-known fact what I'm about to write down. It's elementary, as you'll see, and I don't know where it was first noticed. I think I maybe first saw it in a paper of Percy Diaconis and somebody else. But it's by now well known in the sort of probability community, at least, in a sense that only probabilists are the ones who think that it's an important fact. So it's a little proposition about this function, that it's a positive function. I wrote greater than or equal to 0, but actually strictly greater than 0 for real x. So I will now sketch for you the proof of this in one phrase or two phrases, and leave it as a homework exercise to carry it out. And it's so easy that you don't even have to go home. You probably will do it while you're listening to the rest of the talk. So here's the proof. Well, one way of showing that an infinite series is positive is to show that each of the terms is positive. That works, almost. It works when x is greater than or equal to 0. So, I mean, to begin with, it may not be positive because there's a difference. This is positive, obviously. That's positive. But you have a difference of two things. That may be negative. And in fact, those things will be negative for some n's when x itself is negative. But it's easy to see that when x is greater than or equal to 0, each of these terms is non-negative. And so at least for positive x, or non-negative x, you have a series which is term by term non-negative. It would be, I think it'd be hard put to figure out why this is true for negative x, because it's no longer term by term, but you don't have to do any work because of this. So, and then use this property 1. So that's the proof. Okay, now, being trained as a probabilist, once you have a function which is non-negative and rapidly decreasing, at least decreasing rapidly enough that it's integrable at plus and minus infinity, and decreasing fast enough that you can take the two-sided Laplace transform, then of course nothing else you can think of next other than thinking of this in more probabilistic terms, which is what we do. So we have so this strange thing is, this particular function is a positive rapidly decreasing function of x on the both plus infinity and minus infinity on the real line. So it's almost a probability density, except that it's not normalized. So you can normalize it. So some positive constant, that constant is 1 over the integral from minus infinity to infinity of this function. Is the probability density of some random variable that I'll call x. So this first of the lectures, I've often given some version of it as a kind of math colloquium. And since in that setting, a lot of the audience is not in probability, and so I have to kind of either apologize or replace some probabilistic notation. But since this is a probability statistical mechanics conference, I don't think I have to do that. So I can now use the fact that so if I multiply this integral by c, then that's the Laplace transform of the probability density, and that is the moment generating function of the random variable with that density. So the Riemann hypothesis in that this is no different. It's just written in probabilistic language after multiplying by the constant c, is that the moment generating function, which is just this times c, has only pure imaginary zeros. Okay, so although this is pretty elegant looking from a probability point of view, it's not clear why that helps you much, and that's what the rest of this talk and then much of the other talks is supposed to be about. How because of the Lee-Yang theorem, which I haven't yet discussed, how it might possibly help. Okay, so let me kind of say it descriptively in words and then start writing more precise things. So the point is that there are statistical mechanical models, namely certain types of Ising models and others, as we'll see later, which give rise to random variables I'll call them x tilde. I'm going to try to reserve the use of x and psi for this specific psi and the specific random variable that has that probability density, c times this. And then when I want to talk about something that might be like it or might approximate it, I'll use a tilde. So it gives random variables x tilde, which have exactly the property that we would like to show is the case for this specific random variable and density. Exactly the pure imaginary zeros property for its moment generating function. So this sentence is the basis of this series of talks. And there are, as we'll see, there are a number of such kinds of models. And the first of those will be a certain class of Ising models, and that was the fact that you have this pure imaginary zeros property was proved by Lee and Yang in their theorem. So there's a case of related to some comments from the last talk. Lee and Yang are bona fide theoretical physicists. We know that they're bona fide because they won Nobel Prize for theoretical physics. But the result of that, as I'm going to talk about, really is a theorem, and they really proved it. It's not what they won the Nobel Prize for. They did some other things which were regarded as even more important from the point of view of physics, having to do with parity violation, I guess. I love to give this talk in China because even though by that time that they won the Nobel Prize, they had American citizenships, they were you know, born and originally trained in China. All the Chinese know that very well. I believe the first Nobel Prize to anybody born in China, I think. Okay, so this fact is the basis for this series of talks, and there are a number of different types of models, and we'll talk about them, but the first of those, which we'll talk about for quite a while, is the original theorem of Li and Yang, which has to do with Ising models. So the first of these types of models the first is a theorem of Li and Yang, T.D. Li and C. N. Yang, both of whom are still alive, last I heard. 80s and early 90s, right? T.D. Li and C. N. Yang. I thought Yang was also. No? He was recently. But at that age, you know, you have to check often. I think he, well, all right. I thought he not, well, I don't want to say any rumor mongering. That theorem is from 1952. And it's about the following type of models: finite Ising models with pair ferromagnetic interactions. Which I'll now define for you. Okay, so as I said, so sometimes I give this talk in more of a general mathematical setting. So the notation I use is kind of somewhere in between probabilistic and more general analysis. So I'll define the Ising model in terms of the joint distribution of its basic variables. Little n is going to represent the number of spin variables. It's a probability measure. I mean, formally it's on n-dimensional Euclidean space, but it's actually a discrete measure because the coordinates only take the values +1 and -1. So there's a normalization constant, which is 1 over partition function. And let me leave a space. Then you have, you begin with just basically each of the n coordinates is independently +1 or -1 with probability 1/2. So S sub I represents the ith component of the n-dimensional vector. And that can be -1 or +1. Before you put in the extra Gibbs factor, those have equal probability. So these are just direct, unit direct point measures. So if this is all you had, that would correspond to the infinite temperature case, or inverse temperature of 8 equals 0. No interactions, but of course you're not interested in that. And so it's modified by a Gibbs factor. For the moment, I'm not going to put in a temperature or inverse temperature parameter. It kind of can be absorbed in the couplings, just to simplify the statement. And I sort of have two minus signs, which I've combined to be a plus sign. And so the energy or Hamiltonian function is a quadratic expression in the spin variables. Once you have these, then this would no longer be a probability measure, so you have to normalize it by this 1 over this constant. And the ferromagnetic assumption here is the assumption that these coefficients are all non-negative. So, is it clear what the kind of model? So even though it's written as Rn, that's just that's a little pedantic. The basic variables have n coordinates, which take the values +1 and -1, and the joint probabilities are proportional to this e to a quadratic factor. With the Jij's non-negative, it gives more probability or more weight to those choices where the SIs tend to be the same as each other, as opposed to ones which tend to be different. So if you're a probabilist rather than an analyst, so you think of this as Pn as the joint distribution of plus or minus 1 valued random variables that you might call capital S1 up to capital Sn. Okay, so is the meaning clear? So, so the reason I made this assumption is because this is needed for the theorem of Yin-Yang about the location of zeros. It's a perfectly good model without this assumption, and if you were in the last lecture or that series, then you know that if I was not interested in the Riemann hypothesis on some particular day, but rather in spin glasses, then I would be studying these models where these Jij's are not all non-negative, but some are positive, some are negative, and in fact chosen kind of at random. That would be a spin glass model, but that doesn't seem to be relevant for thinking about the Riemann hypothesis. It's important for other things. Okay, so now I can tell you the theorem of Li and Yang. I guess Yang should be Yang, maybe Yang. So I've been spending quite a bit of time in China in recent years, and I've not learned essentially any Chinese. The only thing that's happened is that I feel guilty about how badly I pronounce things. Yes? Sorry, both? Okay. Yeah, so those things, the web tends to get that news very quickly. And I think Young is the older one, I think, and I believe he's 91 or 92 now. He was the youngster of the collaboration. So here's a theorem. So I'm not going to state it in its most general form. I'm going to state it, even the most general form that Lee and Young themselves did. I'm going to state it in the form that's kind of a slightly special case, which is sort of the one that's most relevant for us, that's closer to looking at these block magnetization variables. So now I have some more coefficients. These are n of them. And those are also non-negative. Those are kind of the coefficients of the block magnetization, or the. And now I'll write it in both kind of analysis notation, and then I'll write it in probability notation. If you look at, so p sub n is this measure in Rn. If I now look at this integral, well, let me start down here. If I look at the expectation of e to the z, if I take a positive linear combination, a non-negative linear combination of these variables which have this joint distribution, that gives me a single variable, and I look at its moment generating function. That's the same as taking this joint measure and doing the corresponding integral. But this is a better way to think about it. I also want to rewrite this as, since it's the moment generating function of this variable, then it's the Laplace transform of whatever the distribution of that single variable is. So I can think of it as integral over the real line of e to the z s z rho n of s, where this is the distribution of summation lambda I si. Okay, so if you're a probabilist, you can forget that thing. You just go from here to here. And the theorem of Lee and Yang, or at least the special case of the theorem of Lee and Yang, is that this moment generating function of the distribution of this variable coming from such a kind of Ising model has exactly this pure imaginary zeros property. Okay, so is the statement of that clear? So now I'm going to write a more or less immediate corollary modulo one little thing, which I'll maybe make a comment about it. I never get around. I think I got around once to checking the one detail, but I didn't write down what I did after I checked it for myself. But so So let me explain the point of this corollary. A random variable x with this particular density, which is actually a nice continuous function on the real line, that's the kind of random variable or probability distribution or density that one would very much like to get the pure imaginary zeros property for. This theorem gives you certain random variables with their distributions, which has the pure imaginary zeros property. It's immediately clear that none of these can possibly be this, because this has a continuous density on the real line. Every one of these is discrete. It has at most 2 to the n values. But it's pretty reasonable that limits of these things will still have this property. And we're going to talk a lot about different kinds of limits that you can explicitly get, some semi-explicitly. But abstractly, if you can obtain as a limit of such distributions with one little technical condition, I'm not even sure if the technical condition is needed, but that certainly makes it sufficient. If you could somehow get this particular density as a limit in distribution of those random variables, then you would basically be finished. So I'm going to state that as a kind of abstract corollary. But don't get too excited, because it doesn't really solve anything, but at least sets up a way of thinking about it. So let F be the class of probability measures on the real line that are weak limits such row sub n's. So let me be a little bit more clear, maybe. So for each n, you can consider an Ising model with n variables, and where you've chosen somehow some couplings which might depend upon n, and you've chosen some averaging coefficients, non-negative, which may also depend upon n. So you have the distribution. Each row n is a distribution of something that looks like lambda I super n, Si super n, where for that n spin Ising system, these averaging coefficients are non-negative, and the coefficients, the coupling coefficients are also non-negative. So that guarantees that you have the Liang theorem applies to that particular size n Ising model. So these are the things that can be approximated in distribution by such things. Now let me add the little technical thing. You might ask, is it enough simply to have limit and distribution in the usual probabilistic sense? I think actually that is enough, but to be safe, I know that if you had one little condition, then that's enough. To be safe, also assume that the second moments are bounded as n goes to infinity. That is to say, assume that you have a sequence of these models with these assumptions, and they converge in distribution, and the sequence of second moments of these variables stays bounded and goes to infinity. That little extra technical thing is enough to guarantee that in the limit, you will still have this pure imaginary zero property. You use some kind of standard complex variable methods to do that. I write to be safe because I have the feeling that you don't actually even need this extra condition, but it's a pretty mild condition anyway, so. Okay, I guess I'm supposed to conclude this. Oh, that's a definition. Now I want to say something about this. Well, the point is that anything which can be approximated in this mild way, limit distribution and finite bounded second moments, then it will also have this pure imaginary zero property. Therefore, all you need to know is that this particular density, this multiplied by C, belongs to this class. Can people see down here? If C psi of x dx, if that measure corresponding density is in this class, then the Riemann hypothesis follows. As a consequence of the Liang theorem and this kind of approximation scheme. Okay, so so let me first, so I said this already, let me kind of repeat it, slightly different words. This by itself kind of sets the stage for what we're going to discuss. I think it's not, so it's important from that point of view, but don't get the wrong idea. I don't think there's any chance whatsoever that the Riemann hypothesis will be solved by sort of characterizing what this class is in some way other than what's defined here, so that we say, oh, F is the set of all things that look like the following, and this thing is one of them. I don't believe that is possible. I mean, it's theoretically possible, but I don't think it's actually possible. But it kind of sets the stage. That is, there's no reason to understand this whole thing. All you're interested in is whether one particular probability density belongs to it. And so that seems more useful to think about. Don't try to understand the whole thing. Think about whether there's a way of showing this belongs to that class by simply doing some sequence of approximations. So I will state that as an open problem. Find a sequence of such Ising models so there's not just the coefficients, but also the coupling coefficients of the Ising model, but also the averaging coefficients for the spin variables. That works. Or said a little bit more probabilistically, i.e. obtain the specific random variable x with a specific distribution, right? The x was the one with this this probability density with that formula. That limit and distribution of such, I'll call these block magnetization variables. That is averages of Ising spins with non-negative coefficients. So that is to say, don't try to understand that F kind of in its entirety. You just need to find something that works. So I have two choices now. I was thinking, I had originally been thinking of having a break now, but I know there's somebody who actually has to leave a little bit early. So this is about 2/3 of the way through anyway. So if you don't mind, I think I'll just continue and end a little early. Now you have to stay as long until. Okay, so I don't want to continue under false pretenses. As far as I know, unless something unexpected happens, I won't announce on the 5th lecture that here is the solution of this open problem, because I won't. It won't have been obtained. But I'm going to talk. I'm going to talk about towards the very end some ideas of well, all along, we're sort of working our way towards where you might look for things like this that could possibly work. And one of the things in the background will be that we know that besides this general complicated formula, we know a much simpler formula about the tail behavior of this density, and so we'll be interested in whether you can get limits of this sort which maybe have that kind of behavior, or at least are working their way towards that kind of behavior. So a lot of what we'll be doing will be just different examples of block magnetization variables from different Ising models, where in the first few cases you can explicitly write down what the limiting distribution is or express it in terms of some known stochastic process, and then some ideas that they suggest about where you might be looking. And one of the points that I'll try to make is that I've been thinking about this kind of thing for a long time, but so let's see, a long time is a long time. I'm not as old as Lee and Young, but I'm getting there. So I guess something like 40 years maybe. So I'd say roughly for the first half of that period, I kind of knew this, but I thought it was interesting, but not very likely to succeed, at least for me, because I kind of assumed that something so strange looking, probably you would need to choose some Ising models that were related, that had some number theoretic content or something of that sort. Since I don't know any number theory to speak of, I wouldn't be able to do that. But I'm going to try to make suggestions which is I kind of began thinking might be the case after only about 20 years. That maybe that's too pessimistic, and it might be that some model or sequence of models with perfectly natural, interesting statistical mechanics, physics sort of behavior might in fact be the right places, and something that even though this looks weird, it could come up. And I'll try to give a little bit of justification for that way of thinking. So, a lot of what we'll be doing will be doing examples where you can say something about limiting distributions of block magnetizations and try to see what they suggest about where to continue looking. Okay, so in fact, the next thing I'll do is simply state three cases where you can, the first two you can get explicit explicit formulas for the limit. The first case is completely trivial. The second case is semi-trivial. And then a third case where you can't get an explicit formula, and that's much more recent work. It's quite non-trivial, but at least you can get something explicit about the tail behavior, the thing that you would like to be, what is that? The thing that you would like to look like this. In that particular case, it doesn't look like that, but as you'll see from the first three examples, it's moving in the right direction. So I'll mention those now, and then I'll give you one psychological reason for why, even though this looks so complicated, it can arise in simple, relatively simple settings. Unfortunately, the setting it arises that I'll mention to you doesn't seem to have anything to do with the Ising model, but maybe somebody here can find some relation. Okay. And that will be more or less everything for today. So the next topic is some examples, and this this is going to be carried out in detail in I think it was lectures. These examples in lectures maybe 3 and 4. Lecture 2 is actually a proof of the Liang theorem for Ising models. So those are what I call C tilde, psi tilde. So in this case, these tildes, I don't mean the original Ising model, but I mean the limiting densities for block magnetization variables from Ising models that you can get. These aren't, I have the tilde because they're not this one, which is the one you want. They're whatever they are. So I'm going to do 3 examples and basically just sort of state the examples, explain a little bit about them. And these will be discussed in much more detail. Well, the first one is completely elementary, and as you'll see, and that everybody here, if you've had, I don't know if there's anybody who's not at all a probabilist, but for this one, all you need is undergraduate probability. So here's the first example. What is the simplest possible Ising model with n variables? Well, it's the one where you don't have any interactions at all. That's okay. It's okay for the Liang theorem. So all the coefficients identically 0. So what do you have then? You have the Ising model is just independent coordinates which take the values +1 or -1 with probability 1/2. And now you want to look at a sum of those variables with some positive non-negative coefficients. Well, it's natural to take the sum to be all the coefficients the same. In fact, that will be the case, I think, in all 3 of these examples. The coefficients are the same. But if these are independent variables, you know what coefficients to take. You're adding n independent plus or minus 1 valued random variables. If you take that sum and divide by square root of n, that is the celebrated central limit theorem. In fact, it's more or less the original central limit theorem, which was done for 0, 1 valued variables. It's de Moivre and Laplace. When is that from? Several hundred years ago. So in that case, you should take the coefficients all to be the same and of the form 1 over square root of n, because you're adding n independent variables. The variables have mean 0, equally likely to be plus 1 or minus 1, have variance 1. And so you normalize, you don't have to subtract any means. You normalize by dividing by the standard deviation, which is the square root of n. So if you take that, then in that case, this sum just becomes the sum of n independent mean 0 variance 1 random variables divided by square root of n. That converges to a standard normal distribution. That's the undergraduate level. At least in France, it must be undergraduate level. In the US, I'm not sure. It's probably not. But in Shanghai, it is. So that's the central limit theorem. I'm not being fair to the U.S. entirely, but I'm allowed to. And so you get a limit, and the limit is a standard normal density function, which is 1 over square root of 2 pi e to the minus x squared over 2. Okay, so this is, undergraduate level fact. And at least it shows that you can get nice densities in the limit, even though you start with discrete variables. So that's good. It, of course, isn't this. And it kind of badly misses having this kind of tail behavior. It goes to 0 quite rapidly, like e to the minus x squared, but not like e to the minus e to the x. You'll see as we go through the two other examples that each of them will be rapidly decreasing and more rapidly decreasing successively, but none of them, including the last one, will be at that amount of rapid decrease. Okay, so okay, the second example is not undergraduate level, but is easily could be, well, you could actually do it at undergraduate level. I mean, it's not normally done, but it's easy enough that you could do it. It's the next simplest type of Ising model. The next simplest type of Ising model, instead of taking all these coefficients to be 0, you take them all to be the same as each other. That's called the Curie-Weiss model, and the Curie is Pierre Curie. Okay, now when you take them all to be, this is related to a comment from the last talk also, when you take them, although that was a spin glass setting, in this case, the ferromagnetic setting, when they're all equal, their n squared coefficients, you better not make it a fixed constant or there would be too much interaction, there would be too much dependence. So you better make these depend on n in the right, getting smaller with n in the right way so that you get a sensible limit. The right way turns out to be a constant over n. And the constant that you multiply there is actually the inverse temperature parameter, the way I've set things up. And in this case is the first place you see that when you have a temperature parameter, it's important to pick the right value, namely what corresponds to the critical point of the Ising model. And one knows what that is exactly. In this case, I'm going to just call it a certain critical value. So if my notation is right, it's actually 1. but I'm always nervous that I've missed a factor of 2. I'll just call it, it's a specific universal number, which I think is 1. It's not 1, it's 2 or 1/2. Yeah, that's, I'm being safe. So this is called the Curie-Weiss model. So in this case, again, as I said before, in all of these 3 cases, in fact, all the cases will, well, all these 3 cases, these lambda sub i's, which could in principle depend upon the index I, actually won't. They'll be the same for all of the spin variables. But they will depend upon n in some appropriate way. Here, it went to 0 like square root of n. That's basically because in all the cases, you basically want to normalize, there are mean 0 variables. You want to normalize by dividing by the standard deviation, the unnormalized standard deviation. And the variance here was growing like n, so you have the square root of n. In this case, at the critical point, the variance is growing like n to the 3/2. And so you divide by the square root of n to the 3/2. That may not be obvious to be, but that turns out to be the case. So that standard deviation grows like n to the 3/4. And in that case, you can actually get an explicit limit, and we'll do the derivation in, I think it's maybe lecture 3. It's not very hard. And the limiting density you get turns out to be constant times e to the minus some other constant times x to the 4th. Again, this is some universal number which may be 1/12. But I'm afraid to write it down. And we'll derive this completely, and it's not difficult. The third example is much less, not so simple. That's what's called the standard. That's the standard nearest neighbor, 2-dimensional. D equals 2. What I was calling 2 capital D before, 2 spatial dimensions. Ising model. So I'll just tell you or remind you what that is. In this case, the sequence of n's you should think of as being the square of some other natural number, because the model is really indexed by points in a 2-dimensional integer lattice. So I and j are points in say in a square subset of the 2-dimensional integer lattice. So they're m squared spin variables, and the coefficients of the standard 2-dimensional Ising model you can think of as being, I'm leaving aside the multiplicative constant. 1, if these points in the 2-dimensional lattice are nearest neighbors. In Z2. And 0 otherwise. So this is the first case where the couplings are not trivial. Here they were all constant, either 0, completely trivial, or constant, relatively trivial. But here they have geometric structure. So just like in this case, there's an overall coefficient, which is the inverse temperature. And like in this case, you want to take this temperature to be at its critical value. I'll call it beta c hat. It's a different number than that. that is also a universal number, but it's something like hyperbolic tangent of 2 or hyperbolic cosine of 1/2 or something like that. In this case, here the variance grew like here the variance grew like n, so you normalize by square root of n. Here the variance grew like n to the 3/2, so you normalize by the standard deviation square root of n to the 3/2. Here the variance grows like something like n to the 1 plus 7/8, which is the same as. Yeah, well, it hopefully was consistent with what I'm about to write down. Anyway. So that means the variance would be 15/8. Yeah, 2 minus 1/8 is probably. In this case, this case is quite non-trivial compared to the other ones. And the thing I'm going to write down in a moment is relative, within just the last few years. I mean, it's been known forever, a long time, that what it should be, but only been proven not so long ago. One can show that you do have a limit, and that the limit has a nice density. The formula is not known explicitly. It's possible that someday it might be known, perhaps. But one does actually know what the tail behavior is like, and that turns out to be, looks like e to the minus some constant. This is yet another constant, x to the 16th power. So this is much more recent. This is work Federico Camilla, who's in the audience, Christophe Garban, who I don't think is in the audience, but no, somewhere in France. And this will appear rather shortly in the IHP, Annales de l'IHP. There are other things in there, but this particular thing is also there. Okay, so and we'll talk somewhat about this in, I think it was maybe lecture 4. I'm certainly not going to do the whole proof. For one reason, there wouldn't be enough time. For another reason, I would have to consult with Christoph for a considerable period of time before I'd be willing to try to. But I probably sketch a little bit related to it. Okay, so I want to finish with one main comment, which I mentioned before, which has to do with this strange formula. Let me go over here. So so remember that, I just erased that you're looking for something. If you got the right thing, it would have a tail that looked like e to the minus a constant e to the 2x. None of these three examples does that, but it is somewhat satisfying that as you go to more complicated examples, the tail goes to 0 faster, so it's going in the right direction. So Zeno's paradox says it will take infinitely many attempts before one gets to the right thing. So here's the Here's the general idea. Okay, so each of these three examples is a fairly natural Ising model. So the example is to find some other natural Ising model. In the last two of the three examples, in order to get some decent limit, you had to take the model at its critical point. You had to take the inverse temperature to be the critical temperature. And so that's probably a good idea. I'll be a little more general in that, maybe not right at the critical point, maybe near the critical point in some precise sense. So these are nice examples, but they're not the right one. You want to get this real one, the one from the Riemann hypothesis. Let me say something I won't write down. So as Francesco Guerra pointed out, the power that appears here is related to one of the standard critical exponents of the Ising model. Similarly, the power here is related to the mean field or Curie-Weiss critical exponent. The fact that the thing you want decays like e to the minus an exponential rather than e to the minus a power suggests that the critical behavior of if there's a natural model should be a sort of unusual one, in that it's, should have unusual behavior as you approach the critical point, or at the critical point as you approach the critical point. That may be a very useful indication of where to look. It also suggests that the normalization, which keeps on getting closer to n, you don't want n because n is, you divide by n is when you get a magnetization, which would be 0 at the critical point. But maybe you want to divide by something close to n divided by log n, or n divided by log n to a power, or something like that. That also may give you hints as to where to look. Probably a, I don't know, special type of critical point. To get okay, but now I want to address the following question, which I'll give a kind of answer, but it's more of a psychological answer than a mathematical answer. Why should we have any reason to think that there'll be some kind of natural Ising model which would give rise to this strange-looking thing? So let me ask that question. Can such a strange psi of x arise in a natural way? So I want to give a slightly positive answer to that question. Maybe. I'll say more than that. I'll write more than that. So what I'm going to write down, it's a known fact, not done by me, by other people. It's known in the probability literature of the I don't know, not sure when it was first noticed. Sometime in the last 10, 15 years, something of that sort. It's a rather fairly natural probabilistic setup in which almost exactly this thing arises. So the point of this example is that this thing that at first glance looks very complicated can arise fairly naturally. So here's the setup. Probably somebody in the audience knows who first did this, but you can find it in various there are various survey articles about relations between zeta things related to the zeta function and probabilistic models. Here's the fairly standard object to look at, or one of them. This is the following stochastic process. It's a properly scaled Brownian excursion. S is a time variable, so roughly speaking, it's a more sort of Brownian motion in ordinary Brownian motion in time. You first make a Brownian bridge by forcing it to come back to 0 at time 1, and then you sort of force it to be strictly positive between 0 and 1, and then you maybe normalize it properly. There are various ways of defining it. Anyway, what you get is one of the standard definitions of a Brownian excursion. It's a stochastic process that starts at 0, ends at 0, and is strictly positive in between, and closely related to Brownian motion. All right, just 1 second. Okay, let M1 be the maximum of this Brownian excursion. It's a continuous, it's a random continuous function on 0, 1 that has a maximum. So the statement is that the distribution of this, so this is a fairly natural object. The statement is that the distribution of this is very closely related to this peculiar function. So first, notice that, so this is strictly positive. We want something which can be both positive and negative, so take the log of the maximum. Okay, and now center that by something. So I add or subtract a constant. I can think of that as multiplying this by a constant. And the right constant turns out to be square root of 2 over pi. So now I have a random variable which can be both positive and negative. This random variable will have a probability density which is almost exactly the same as this weird thing. It only differs by a simple exponential factor. So it's not even, but it misses by a kind of an exponential factor. And then, of course, it has to be normalized. I'll call that C prime. Okay, so that, I think, is a correct statement. I don't have a reference at hand, but I think there are lots of papers. I know I think this thing, for example, there's a paper by 3 or 4 probabilists, one of whom is Mark Yor, from, I don't know, 10 or 15 years ago, which has a whole bunch of things, I think, including this fact. So I only have the point of this is that maybe one shouldn't regard, as I did for 20 years, this as so weird looking that it can't arise in a natural way. Here's a relatively natural way where basically something extremely close to it, arises. So perhaps it could arise from a natural Ising model at its critical point. That's a positive comment about this remark. The negative comment is, well, here's a nice place where it arises. Unfortunately, this doesn't seem to have anything whatsoever to do with Ising models. What has this example, I mean, this Brownian excursion example? And I don't have an answer to that, but maybe there's some funny relationship between Brownian excursions and Ising models, which would allow somebody who understood that to look at this and say, oh my God, why don't I do such and such? But I mainly brought it up for a different point. The different point is that even though it looks weird, it can arise naturally. So maybe there's an Ising model, or one of the other types of models that we'll talk about later on, like XY models, where it could also arise naturally. And in that setting, you already have Liang theorems or Liang type theorems to work with. There isn't a Liang theorem that you can apply to this setting that I'm aware of. Okay, so I think I'll stop there. Thank you.